Professor Isha Medilata from LG Institute of Engineering and Technology. We have already started with our content, with our syllabus, and the module which we have started is superconductivity. Until now, we have discussed what basically superconductivity is, what is critical temperature, how resistance varies with temperature, and what are the properties of superconductors. Today's session, we are going to discuss another important topic, which is types of superconductors. Before I start with the topic, let me just discuss briefly the three important factors which are used to define a superconducting state. The three factors are critical temperature, critical magnetic field, and critical current density. You can see that critical current density and critical magnetic field are interrelated. Why? Because if current increases, magnetic field is going to increase. So let's see on what basis are the types of superconductors classified. So they are classified on the basis of critical temperature and they are classified on the basis of critical magnetic field. Let us see how they are classified on the basis of critical temperature. So starting with the first one, that is low temperature superconductors. They are also known as LTS. Let's see what low temperature superconductors are. So they are the superconductors which use liquid helium as a coolant to achieve superconductivity. Why specifically liquid helium? Because liquid helium has temperature value as low as 4 Kelvin. So they use liquid helium to cool down and achieve superconductivity. There are many examples of low temperature superconductors, but mostly they are known as niobium based alloys. Some examples of low temperature superconductors are NdTi, which is alloy of niobium titanium. Then you have Nd3Sn, which is an alloy of niobium tin. Then you have mercury, vanadium, zinc. These are some examples of low temperature superconductors. Let us move on to the second category on the basis of critical temperature, and that is let us move on to the next category on the basis of critical temperature, that is high temperature superconductors, also known as HTS. What are high temperature superconductors? These are the materials which have critical temperature above the temperature of liquid nitrogen. Liquid nitrogen, as we know, has a temperature of -195 degrees Celsius or 78 Kelvin. So they are materials which have a temperature above 78 Kelvin. Superconductivity was discovered in the year 1911. Till the year 1986, that is 75 years, during the span of these 75 years, there was an alloy of niobium and tin, that is Nd3Sn. It recorded the highest temperature of 23 Kelvin. 1 year later, in the year 1987, an alloy which consisted of lanthanum, yttrium and other rare earth metals was discovered, which had a critical temperature more than Nd3Sn. It had a temperature of 30 Kelvin. In the same year, another compound was discovered, which is commonly known as a 1,2,3 compound. Why is it known as a 1,2,3 compound? Because it is an alloy which consists of yttrium, barium, copper, oxygen. So it has the composition Y1Ba2Cu3O7. So basically it is a cupate. You can say it's a ceramic compound which recorded the highest ever temperature around 93 to 95 Kelvin. Let us see some more examples of high temperature superconductors. So starting with YbCO, that is yttrium, barium, copper and oxygen, having a temperature 93 to 95 Kelvin. Then we have an alloy which consists of mercury, barium, calcium, copper, oxygen, having a temperature around 130 to 135 Kelvin. Lastly, there are lanthanum compounds, basically ceramic compounds that have critical temperatures as high as 300 to 500 Kelvin. This was a brief about high temperature superconductors. Now let us see what is the classification based on critical magnetic field. What is critical magnetic field? It is the minimum magnetic field which destroys the superconducting state. So that is why we call it as an important factor. So basis on critical magnetic field, the first type of superconductor is type 1 superconductors. Let's see what type 1 superconductors are. Before I start explaining the graph, let me just brief you what Mesmer effect is. So Mesmer effect says that superconductors are diamagnetic in nature, and we had proved using an equation where we derived the ratio of magnetization with respect to applied magnetic field as -1. What does that mean? If you magnetize a superconductor, if you apply magnetic field to a superconductor, it will repel the magnetic field. So if magnetic field is applied in this direction, magnetization will be in the opposite direction. And that is the reason magnetic susceptibility, that is chi m, we exactly got the value as -1. Now here in the graph, I have taken applied magnetic field on the x-axis and the magnetization on the y-axis. Instead of m, we will be using -m because the ratio of m by h is -1. So starting with the graph, you are increasing the value of applied magnetic field, the value of magnetization increases but in the reverse direction. Now this straight line will not continue till infinity. It will continue only till a value that is Hc. See what happens when the critical field is achieved. The magnetization suddenly reduces. Or you can say, earlier the field lines that were being repelled, now they start passing through the superconductor. So you can say in this region of right angle triangle, we say our superconductor is in superconducting state. Any value of magnetic field which is above Hc is known as normal state. That means resistance is not zero. Let us discuss some properties of type 1 superconductor. They are called type 1 because they have only one critical field value. They are called soft superconductors. Why soft? They are not soft to touch. They are called soft superconductors because their superconducting state can be destroyed easily. Next we have the transition from the superconducting to the normal state is sudden. So we have seen in the graph, gradually the magnetization was increasing and suddenly it drops to minimum value. So we say the transition is sudden. Next, they allow field penetration easily. So with a small value of magnetic field, they can move to normal state. They exhibit perfect Mesmer effect. So in this region of 0, starting from 0 till the value Hc, we can say that all the magnetic field lines are repelled, and hence we say our superconductors behave as perfect diamagnets, and so they exhibit perfect Mesmer effect. The graph shows a reversible transition. Why? Because if you are increasing, suppose you increase the applied field by 1 unit, magnetization will increase by 1 unit in the opposite direction. If you reduce the value of applied field, magnetization will also reduce. So we say the graph is reversible. Because they apply field penetration very easily, and because they also have low temperatures, they do not have wide applications. They are used in limited applications only. This was about type 1 superconductors. Now let us move on to the next category, that is known as type 2 superconductors. Starting with type 2 superconductors, again I will be explaining with the help of a graph. Same like type 1, we have taken applied magnetic field on the x-axis and magnetization, that is -m on the y-axis. Starting with the graph, you increase the value of applied field, magnetization will increase but in opposite direction. Now let's see what happens to this graph. This graph, instead of suddenly reducing, it gradually reduces. That means I am just trying to say the magnetization is gradually becoming zero. So till a point which is known as Hc1, that is the lower critical field, you see your graph is a straight line. So till this value, our superconductor is in perfect superconducting state. But what happens beyond this point? Suppose I increase the magnetic field beyond Hc1. See what happens. Gradually magnetization reduces, and in this span we say our superconductor is in vortex state. I will be discussing what is vortex state shortly. And if you further increase your magnetic field beyond Hc2, that is known as the upper critical field, your superconducting state is lost and your material will convert into a normal state wherein resistance is not zero. Now let me just brief what vortex state is, then we'll be discussing the properties. So vortex state is also known as mixed state. Let me define what vortex state is. It is basically a thermodynamic state of a material which is characterized by coexisting resistive and superconducting subregions which can be around 300 nanometers apart. What is the meaning of this statement? This means in this state, your superconductor has both, it follows both the possibilities, that is partially it behaves as a superconductor and partially the resistance increases. Let's understand with the help of a diagram. In the diagram you can see the black lines indicate the applied magnetic field. The red lines indicate that magnetic field is not allowed to pass through the superconductor. But this is correct till the value Hc1. What happens in this same diagram after Hc1? After Hc1, if you still increase the magnetic field lines, they penetrate in the material in the form of tubular structures. So, according to this diagram, I can say that some magnetic field lines penetrate and others are repelled. So, my superconductor will behave like a sieve. It will allow only some of the lines to pass through it and some of the lines will be repelled. So this exactly means vortex state, wherein resistive and superconducting subregions are together. Now let us discuss properties of type 2 superconductors. With the first one, they have two critical field values. That is the reason they are known as type 2. We have lower and upper critical fields. Next, they are called hard superconductors because it is difficult to destroy the superconducting state. Why? Because gradually the magnetization reduces. Next is the transition from superconducting state to normal state is gradual. It is not sudden. Slowly the magnetization reduces. Field penetration is not easy, again because transition is gradual. They exhibit partial Mesmer effect. Why partial Mesmer effect? Because if you consider the vortex state, you can say that some field lines pass through it and some are repelled. So they behave like a sieve. Next is the graph shows an irreversible transition because in the vortex state, some magnetic field lines have already started penetrating, so the graph becomes irreversible. Because the field penetration is difficult, also they have higher critical temperatures, so they are used in wide varieties of applications. I complete the topic types of superconductors. Now let us discuss some numericals related to this chapter. Briefing you, the formulae we have already covered with isotopic effect wherein Tc and isotopic mass are related. Then we have studied the relation of critical temperature and critical magnetic field. We also have studied the relation of critical current and critical magnetic field, critical current density and critical magnetic field. So keeping all these formulae in mind, I start the first numerical as for mercury of mass 202, value of isotopic constant is 0.5 and critical temperature is 4.2 Kelvin. You have to find the transition temperature for mercury of mass 200. So here two different mass values are given. You are also given the value of alpha and you are given one critical temperature. That means M1, M2 is given, isotopic constant is also given and critical temperature, that is 4.2 Kelvin, one of the critical temperatures is given. So we will be using the equation Tc1 M1 raised to alpha is equals to Tc2 M2 raised to alpha. Substituting the values in this equation, we get the answer as Tc2 is equals to 4.2209 Kelvin. Moving on to another type of numerical. Here, the critical temperature of niobium is 9.15 Kelvin. At 0 Kelvin, critical field is 0.196 Tesla. You have to find the critical field at 6 Kelvin. So Tc is given. What is critical field at 0 Kelvin? It is denoted as Hc0 or Hc0. Also a value of T is given. So according to the question, we have Tc, we have T, we have Hc0, we have to find Hc. What is the equation we will be using? We will be using this equation, Hc is equals to Hc0, 1 minus T by Tc the whole square. So substituting all the values, we get the answer as 0.1117 Tesla. Moving on to another category of numerical, wherein we have to find critical current for a superconducting wire of lead having a diameter 1 mm at 4.2 Kelvin. Critical temperature of lead is 7.18 Kelvin and critical field at 0 Kelvin is 6.5 into 10 raised to 4 ampere per meter. You are not directly given the value of critical field here. You are given what is T, what is Tc, you are given Hc naught. You are also given the diameter of the wire. So to find out Ic, we have to first find out what is the critical field. So first we will be using the formula Hc is equal to Hc naught 1 minus d by dc the whole square. Using this formula, substituting all the given values, we find the value of Hc, that is critical field, as 42.758 kiloampere per meter. Now we know the relation Ic is equals to 2 pi r Hc, and we already have derived what is Hc. So substituting the given values and the derived value, we get the answer of Ic as 134.26 amperes. One more numerical from the chapter. Critical temperature of a superconductor when no magnetic field is present is Tc. You have to find the temperature at which critical field becomes half of its value at 0 Kelvin. So you are given the value of Tc as Tc only, no numeric value is given. You are also given a statement that critical field means Hc, it becomes half of its value at 0 Kelvin. What is the value of critical field at 0 Kelvin? Hc naught. So according to the question, we have Hc is equals to Hc naught by 2. We know the equation of Hc as Hc naught 1 minus d by dc the whole square, wherein we can cancel out Hc naught from both the sides, and we finally get t by dc the whole square as 1 by 2, or we can say t is equals to 0.707 Tc. This was just a glimpse about types of superconductors and some of the numericals from the chapter. I will be starting with the topic mechanism of superconductivity in my next video. Till then, take care. Thank you.